Hi, everyone. Welcome to my workshop about scientific discoveries that inform metaphysics. So first, I'm going to introduce myself. My name is Jacklin. I've been a debater for a very long time, but I've also, more importantly, studied physics and have a master's in physics from the University of Manchester. And I've taken modules in metaphysics, and I've also read extensively about the subject. So first, a disclaimer. I've not been in contact with the ORCOM about what type of motions are going to come up in the International Metaphysics Open. So I'm not sure if anything I'm about to tell you is going to be fully applicable or useful in a debate context. I personally can't imagine when I'd ever use quantum physics in a motion, but hey, like there's a first time for everything. And so hopefully you just have the intellectual curiosity to understand or to learn about what contemporary physics has to say about the nature of reality. And so, with that disclaimer out of the way, do I know what I'm talking about? I probably should have rephrased this question to maybe say, am I the definitive source of physics and metaphysics? The answer is no. Please do not use my workshop as the end all and be all of all metaphysics and science. So especially with the stuff that I'm talking about, because they have been such contemporary findings, there's still a lot of debate within the physics community about the correct interpretation about a lot of these findings. So the kind of stuff that I'm going to be talking to you about may come across to you as a bit reductionist, especially if you are from a physics background. But this presentation is really just to give you a brief overview of core concepts that I find really interesting and theories that are easy to grasp and apply as a non-scientific audience. There's lots of really interesting ideas in physics. Not all of them are friendly to people without a mathematical or scientific background. So that kind of just means there's a restrictive cap to the depth and balance I can give to the theories presented. But I think the aim of my presentation is to give you a kind of substantially rich look into contemporary physics and what it has to imply about the nature of reality without being patronizing, but also without being bogged down by the mathematical details that a layman audience wouldn't understand. So first, core concept that I think is very, very interesting. It's called wave-particle duality. So I think this is one of the most impactful theories to ever come out of contemporary physics. So some of you may have heard that light is both a particle and a wave. I just want to highlight how bizarre this concept actually is. What we're basically saying is that in some contexts, light behaves as a particle, and in other contexts, it behaves as a continuous wave. The reason why it is bizarre is because these two things are contradictory concepts. One is a discrete point in time and space, and the other one extends continuously across space. So if you look at the graphics on the right-hand side, you can see that a particle is something that is just basically a point, while a wave is something that is kind of has a plane where it moves throughout space. So imagine a singular raindrop versus a entire wave at the beach crashing onto the beach. So those two things are contradictory concepts. And it's very strange that an object can exhibit characteristics of two profoundly different things. What we found is not that only light can exhibit particle and wave characteristics, but it's also lots of other things. So lots of quantum objects, such as electrons, such as quarks, they can also exhibit particle and wave qualities. So just to explain how strange this concept is, I'm going to go through an experiment that some of you will be familiar with. It's the double slit experiment. So lots of high schools around the world teach this experiment. Basically, what you have is a screen with two slits. So imagine two very thin slits in that screen that allow things to pass through those slits. And behind the screen with two slits is just, another screen that catches anything that travels through the first screen. So according to according to classical physics, electrons should travel through the screen with two slits and land onto the optical screen laying behind it. And it should just form a very predictable pattern. So because classical physics says that electrons should behave as particles, they just travel in straight lines unless there's an external force acting upon them. So electrons should just go through these two slits, travel in a straight line, then land on the optical screen forming these two dark bands. And so this was the behavior that was noted for years. However, what we noticed is that if the slits were made small enough and close enough together, what we observe is the right-hand scenario. So this is called an interference pattern. So it's basically this pattern of alternating light and dark bands. Without being bogged down in the details, basically what this implies is that the electrons are diffracting through the slits and interfering with each other, just like waves. If you don't remember anything from A-level physics or GCSE science, you just need to know that the left-hand side suggests that electrons are particles and the right-hand side suggests that electrons are waves. So what we could see is that electrons can behave as both. So it can, in some contexts, exhibit particle-like behavior, and other contexts exhibit wave-like behavior. So this is already quite strange, since it seems to change its intrinsic nature depending on the experiment that it's that's taking place. But this is not where the weirdness ends. So that's not all. Let's just say we set up the same experiment again. And so this time we'll watch the experiment taking place. So we'll just, the entire time the experiment is taking place, we'll just look at it. What we see is that actually, if we observe the experiment taking place in front of us, the electrons almost get shy and they go back into being particles, which is very strange because we haven't intervened in the experiment at all. We haven't put our hand in front of it. We haven't changed any of the variables in the experiment except for passively observing it. So it's very strange that because we have observed it, the particles go back into being localized in a single point in time and space, and they become particles again. And then if we leave the room and just let the experiment run, and then we come back and look at the outcome, the electrons go back to being waves. So it's very strange that just from the sheer act of observation, electrons change their fundamental characteristics into being a particle or a wave. So this has pretty profound impacts about how we envision the world. So scientists always envision the world being split into basically three components. There's the scientist or the observer looking at the world around them. There's a specific thing they're experimenting on, and then there's the environment that can mess the experiment up. So let's say that you want to measure the temperature of a boiling pot of water. There's a scientist or you taking, who's doing the experiment. And there's the experiment itself. So there's the boiling pot of water and there's a thermometer that you're sticking into the boiling pot of water. And then there's the environment that can mess up all your measurements. So this is like the external temperature of the environment. This is the pressure of the environment, whether or not there's wind present, all that stuff. So what we've usually done is that we attempt to correct or minimize the effect of the environment so we can take very clean measurements of the experiment and measure the intrinsic properties of the thing that we're measuring. In this case, it is the boiling pot of water. But what we see here in the previous scenario is that the experiment and the observer seem to be intrinsically linked. So if the observer is involved in the experiment, it changes the outcome. And if they're not, it also changes the outcome. So, so what we see is that we form maybe part of the same system. The observer and experiment are not cleanly separated, and actually we inform each other. This is known as a model known as the participatory universe, in which we actively participate in the universe just by observing it and by existing within it. So maybe classical physics has imposed a very artificial split in the world between the observer and reality. So typically what we thought of as science before quantum physics is that whenever we measured something, we are measuring an intrinsic property of the object. Let's say I, as an observer, look at an apple and I see that it is red. I would ascribe the redness of the apple as an intrinsic property of the apple. I would say that the apple is intrinsically red. But what this experiment has told us is that in actuality, we're not measuring any intrinsic property of the object, but we're measuring the interaction between the object and the observer. It's the same thing with the boiling pot of water, where we're not actually measuring the temperature of the boiling pot of water, but we're measuring the interaction between the thermometer and the boiling pot of water. And so this maybe sounds like kind of a nitpick and kind of a trivial differentiation to make, especially in kind of the examples I've used, but it actually has some very profound impacts in how we think metaphysically about the world. That whenever we do science and whenever we do measurements, we're not actually finding any intrinsic reality. Instead, we are finding relational truths. So we are finding the relations that we have to the reality around us. We are finding relations to one apparatus that we use to measure things and the experiment itself. So I think that's very interesting that in reality, the observer can never really be truly isolated, and a lot of times from the thing that they are observing. So we constantly inform each other and we affect truths about each other. Cool. So the next experiment or the next thought experiment that I can talk about, Schrodinger's cat. I've kind of been forced to talk about this simply because this experiment is just so famous. I kind of want to talk about it because I think number one, is famous. It's probably really important that people understand what it is, but also I think it reveals kind of the uncertainty that exists within interpreting even very, very famous, very impactful scientific findings, such as the Schrodinger equation. So what does the Schrodinger equation find? It basically says that whenever you have a quantum system, basically any system that's very, very small, a quantum system can be like a hydrogen atom, or just like an individual electron. So basically the Schrodinger equation says that a system that is very small can be described as a combination between discrete states. So if you're never sure about what state a quantum system is in, you can describe it as a combination of all the different states it could possibly be in. So for example, if I was going to make what is known as a potential well, so basically an electron can either be in or out of this energy well, I would describe the Schrodinger equation would describe the system as a combination of the electron being in the well and the electron being out of the well. And with that equation, I can calculate the probability of it being in or out of the well. But he says, okay, this is all very good and useful in quantum systems, but let's try to apply this to macroscopic systems. So it comes up with a following thought experiment. So you break up a cardboard box with a trap. Inside the trap, there's a radioactive atom that decays. If it decays, it triggers a poisonous gas to be released. Note that the process of radioactive decay is completely random, so it's not determined by a human. It's not like a timer that's set by a human. It's not determined by environmental factors. Radioactive decay is just one of those things which is like actually intrinsically scientifically random. So you then put a cat in the box and then you close the lid. So because the act of radioactive decay is completely random, you don't know whether or not it has triggered the poisonous gas, and hence you do not know whether or not the cat is alive or dead. If you are going to write a Schrodinger equation for this experiment, you would write it as a weird combination of the cat being alive and dead. And so he says that this is obviously quite absurd. How can a cat be in a weird superposition of being alive and dead? So if you've actually read the original paper, it's actually quite funny because he gets quite evidently angry at the conclusion of his own experiment. He says, obviously, this is really stupid. The cat is not alive and dead. Obviously, it is in one of the two states. And my equation makes no sense if you apply it to a macroscopic system such as this. So what do other people have to say about the Schrodinger equation? So realists actually look at the Schrodinger equation for this thought experiment and say, no, actually the equation represents a really deep metaphysical truth. The cat, when we do not know what state it is actually in a weird mixture of being both alive and dead. Maybe that is not comprehensible to our minds, but it really is in that weird mixture of being both alive and dead at the same time. So this is a school of thought known as realism. There's another school of thought called idealism. Not that these aren't the only schools of thought that exist, but idealists say that Schrodinger's equation doesn't actually reflect reality. Instead, the equation just describes our knowledge of the system. So because we know that this cat can either be alive and or dead, the equation just expresses that and our degree of uncertainty. So it just says like, look, the cat really could be alive or dead, and so it might as well just be in a weird combination between the two. We're not really sure. And the Schrodinger equation really just reflects that. So there's nothing weird that's going on. It doesn't reflect any deep metaphysical truth about what's actually happening. In reality, it just reflects our knowledge about reality. So I think this is an interesting idea. I didn't just like bring this up simply because I wanted to chat about something that people often chat about, but I think it reveals, I think, a rift in how many people think about quantum physics. Lots of people think of quantum physics as purely almost like metaphorically, as kind of like it just represents what we know about a quantum system, and we don't really have anything to worry about because it doesn't really reflect the metaphysical truth or reality of what we're observing or the nature of reality itself. All the equations that we come up with and all the weird findings that we have really can be just chalked down to like our knowledge of the system and the uncertainties associated with it. On the other side, you have realists saying like, no, you have to take these scientific findings quite seriously. I think they actually do reflect a deep metaphysical truth about the reality, and it should reshape our paradigms about how we view reality. So it's really interesting about the relation between scientific findings and reality. Are we just describing our knowledge of reality, or are we describing reality itself? Cool. The next thing that I want to talk about, also, this is also another thing that I have to talk about, simply because so many other people talk about it, and because it's also appeared in Rick and Morty. So I'm basically forced to talk about it. It's a many worlds theory. So first, I want to frame this theory. It's not just something that people made up just because they thought it was a cool thought experiment to go through, but it was meant to resolve a very specific problem in the Schrodinger equation. So the Schrodinger equation, as I told you before, describes a quantum system as a superposition of all the discrete states that quantum system could possibly be in. But once we actually observe the quantum system, we see it in one of the discrete states. So for example, the cat, before I observe it, is both alive and dead. But once I lift the lid, I definitely know that the cat is alive or dead. So what we have here is, I've tried to express it mathematically. Don't be too alarmed if you can't understand. But like basically, the Schrodinger equation expresses the cat as some function of being alive, A, or being dead, B. So some combination of the two. Once we lift the lid, it just collapses straight into a function of A or a function of B. This is a mathematical conundrum, and because this is what we call a nonlinear transformation, this act of collapsing, it's supposed to be kind of mathematically impossible. A scientist called Hugh Everett decided that it was a good idea to resolve this conundrum with the following, that the Schrodinger equation never actually collapses. It is always a complete description, and superpositions persist even at a macroscopic level, but they just exist in different worlds. So the function, so when I open the box, there is a world in which I observe the cat being alive, and there's a world in which the cat is dead. So it goes from a function of dead and alive into a function of alive in world 1 and dead in world 2. So it's trying to resolve that conundrum. But there are many problems with this. Even if you're not really mathematically inclined, you can still appreciate a lot of these criticisms. So if there was a world in which Jacklin observed the cat being alive, in another world, like if I were to, for example, observe the cat being alive, and there's another Jacklin that observed the cat being dead, where is that world with alternate Jacklin? Where does it actually exist? Some scientists will try to tell you some mathematical jargon like exists in phase space or something, but no, seriously, where is it though? And where does the splitting also occur? So does it occur in like big macroscopic actions such as lifting a lid? Does it occur at really microscopic interactions as well? So what level does the splitting occur, and what does probability mean in the context if everything happens? So if I was going to say that there's a 70% chance of raining tomorrow, what does that probability statement actually mean if there is another world in which it definitely does rain, and there's another world where it definitely doesn't rain? So both outcomes definitely do happen. What does the statement 70% probability actually mean? So there's lots of other criticisms as well. For example, it's based on mathematical realism. Hugh Everett takes Schrodinger quite seriously and thinks that he needs to resolve this conundrum because it has a direct correspondence with reality. But probably all of this stuff is irrelevant to you if you're here to do the good debate and have the great discourse. So I think the manual's interpretation is impactful metaphysics because it could be quite interesting ethically. So what does a moral action actually mean if the converse is just going to happen anyway in an alternate universe where things probably carry equal moral value? So if I was going to do the trolley problem, for example, and Jacklin was standing at the lever and she had the choice whether or not to kill one person in order to save five, or she could let the tram or the trolley run its course and kill five people. Let's say this Jacklin right here pulls the lever and decides to sacrifice that one person. What does that moral choice actually mean if there is just going to be an alternate universe where Jacklin didn't make that choice and those five people died? So both universes definitely do happen. What do moral choices actually mean then? So I think this is very interesting ethically and something to talk about maybe at 3 a.m. Not with me though. Cool. Next concept to talk about. Back to the stuff that I really like, uncertainty and complementary pairs. So this was a principle developed by Niels Bohr, and Niels Bohr, if you don't know, is a very influential scientist, was one of the founding fathers of quantum physics. He posited that there were complementary properties that could not be observed or measured perfectly at the same time. So we've explored one of them before. It's wave and particle characteristics. You cannot observe light being both a wave and a particle at the same time because those are contradictory things. What does it even mean to observe light being both a wave and a particle at the same time? Like my brain can't comprehend what that looks like. So we either see it as a wave or a particle. It's impossible to see both wave and particle characteristics at the same time. Other examples of complementary pairs are position and momentum. You may have heard of Heisenberg's uncertainty principle before, that you cannot measure a particle's position at a very high degree of accuracy at the same time you measure its momentum. So what does this mean? This limits our knowability of a system, and it also limits the manifestation of specific properties in physical reality. So what Bauer said is that, look, it means that we can never really have perfect or fully complete knowledge of what reality actually looks like, because we just cannot observe two things simultaneously. Like we cannot observe light being both a wave and a particle at the same time. We cannot know a particle's position and momentum perfectly accurate at the same time. So this really limits our ability to have perfect knowledge of a system. This is not only because our feeble human minds cannot comprehend contradictory ideas coexisting at the same time, but it's also because these traits or these properties do not manifest in physical reality at the same time. So like light just physically does not manifest as both a wave and a particle at the same time. So he says that reality is just constantly in a trade-off between these complementary pairs. So as you can see, like there's actually like I forgot what, I think he made like a society for quantum physicists, and this was their crest, and this is really interesting. So as you can see, they adopted the yin yang symbol as their as that crest symbol, because there's a very nice symmetry to this idea of complementarity, that there are two very contradictory ideas, but they are both equally true, and both are equally needed to understand the full picture of the universe. And so there's a very nice symmetry and philosophical aesthetic to that idea. But also Bauer basically with this idea found that quantum objects were inconceivable in their nature. So quantum objects basically, because they are both light, like they are both wave and particle at the same time, until we actually measure them, they're just inconceivable until we actually interact with them. So he almost sees like the core nature of reality as something like Lovecraftian inconceivable, until we actually interact with it. So interesting idea about the nature of reality, our limits to our knowledge of the nature of reality. Yeah, and the idea of complementary, that contradictory ideas can be equally true. They just probably cannot manifest at the same time. Cool. The next idea and the final idea that I want to share with you is about the non-linearity of time. The way that we think about time is that, we exist in this 3D world and time kind of passes through us. So like we cannot control the passage of time. It just always moves forward. And so something dramatically changed that idea. And so before special relativity, time was seen as a very, very distinct dimension from space, because space you can move around in, time just passes through us. Special relativity, in particular, regards the relationship between space and time. It's interesting here because it basically concludes that time dilates and space contracts when you travel. The effects are only really noticeable at high velocities near the speed of light, but if you're traveling at all, there is time dilation and there is space contraction. So if any of you have ever watched that movie Interstellar, basically a father leaves the Earth in a very high-speed spaceship, and he leaves behind his infant daughter. He has some communication back with Earth, but what he observes is that as he's traveling at a very high speed, time as experienced by people in different reference frames is different. So he experiences time more slowly than the daughter on Earth. So whenever he gets video calls from his daughter, he can see his daughter aging much more rapidly than he does. Simply because when he's traveling so fast, time dilates for him, i.e. slows down. So this is basically what special relativity concludes. So from this, from this theory, we can actually come up with a bunch of paradoxes that are very interesting to analyze and imply a lot of things about the nature of time. And this is one of them. So let's say that Alice and Bob come from two lunar colonies called Alpha and Beta. You can see them here. They decide to go to the middle perfectly between their two colonies and have an arm wrestling contest. They then radio the results back to their colonies, which travels at the speed of light. So you can see this radio tower. It's, conveying the information. It's radioing back the information to Alpha and Beta at the speed of light, so that Alpha and Beta receive the results at the same time. But then there's a spaceship traveling above with a passenger called Clara. Because of her relative motion to the moon, she observes that Beta actually receives the information before Alpha, who is correct. So what you can see here is that there's a paradox because Clara sees time differently than the people on Earth, not on Earth, on the moon. So there are a couple of interpretations to this. First, you can say that there can be no observer independent reality. All realities are basically dependent on the observer and specific reference frame they're in. So this kind of destroys our idea that there is anything like an observer independent truth or a correct reference frame to view things from. But furthermore, it also has very profound implications about time. So basically, because the idea that things happen simultaneously is basically not objective, people have concluded from this thought experiment that there's no real physical difference between past, present, and future, because the idea of simultaneous events just do not have any physical meaning, because what was perceived as simultaneous by Alice and Bob on the moon was not perceived as simultaneous as by Clara on the spaceship. So because of that, what happens in the past, present, future, there's basically no physical difference. And so because of that, loads of people have interpreted this to mean that, maybe time is just a construct that we move through. There's lots of interesting ideas that I won't fully go into, but if you can look them up if you want to. It's called the block universe. So because past, present, and future probably have no physical difference, maybe they just coexist at the same time, that we live in kind of this space where time is just an illusion to us. So a really good example of this is a comic book. So in the comic book, Batman experiences time linearly. So he experiences, losing his parents, becoming Batman, and then fighting Joaquin Phoenix's Joker at the end. So to him, that passage is linear, but to us externally, all of the pages exist at the same time, and we can flip between them, like however many times you want. We can read page 7 over and over again. We can flip all the way up to page 31. So all the pages coexist to us simultaneously. Maybe time in reality is that way as well. We inside the comic book just experience it linearly, but maybe the true nature of time is one where all moments just coexist simultaneously. So there's lots of different variations of the block universe. So a lot of the more philosophically inclined of you would have already said, wait, doesn't that basically mean that we live in a deterministic universe? So it means that we live in a fatalistic universe, i.e. the future already exists, we just haven't experienced it yet. But it doesn't mean that it's predetermined. It just means that it already exists. It's not clear, like it's not clear what it's determined by, for example. But there's other variations of this, which is to say maybe the future doesn't exist, but the past and present exist as a block. So the past moments coexist with all present moments, but the future moments don't coexist with us because they have yet to come into existence. So there's lots of interesting variations of time. What's important to just take away from this is that time is not a linear concept, and it is not one that exists objectively independent of all the people who experience time. Cool. So thank you for watching my presentation. Of course, I can't take questions because this is a presentation. But if you ever have any questions or you just want to chat about the stuff that I talked about, I'd be happy to talk about any of these ideas more in detail with you, or give you some reading materials. I have loads of reading stuff that I can recommend to people. Hit me up on Facebook or on Discord, wherever you can find me. But yeah, I hope you enjoyed this. I hope this was interesting to you. Thanks, everyone.